Everyone, and welcome to Activity 4. Today we are going to talk all about exponential equations and using them to solve for different pieces. So we have a neighbor named Margaret who just won the lottery, and her first payment is going to be $50,000. Now Margaret wants to invest this money in a little account that pays 5% interest over the course of a 20-year period. So if we think about years since 2004 when Margaret won, we have 0 years because 2004 is the year she won. 1, 2, 3, 4, 5, and then 2014 kind of jumps up to year 10. And again, if this is paying 5%, what we could take is, for instance, this first one, we're taking our initial payment amount. She's retaining 100% of that, but then adding on 5% because she is invested it into that account. And then that's getting raised to the T years. And as time goes on, what we're noticing then is each previous amount, we are taking our starting amount and multiplying it by 1.05 to the T power to get each of our values beyond that. So to get year 2007 value, we're taking that previous year and again, retaining 100%, but adding on 5%. So we get that 1.05 as our multiplier. And we see, for instance, this next one would be $57,881.25, and the pattern continues on. So what we notice about the patterns in this table is that the amount that is in the account is 1.05 times the previous amount. And it's increasing each month, but not by a constant amount. So it's not linear each month. So what is this exactly then kind of telling us? Well, again, kind of connecting back to our idea of a geometric, this is going to be an example of an exponential function. And again, these are our multiplicative functions, and they are expressed in that geometric kind of setup, right? A times b to the x power. Our b value is a constant, not equal to 1 in this case. And again, each year is going to be increasing the amount we are multiplying by, and very similar to what we had before. For instance, if we took year 3, which was 55,125, and divided it by year 2, so again, or the months, so we kind of had A2 and A1, we get that multiplier amount, 1.05, to see that rate that we're multiplying by. So again, if we look at different values here, again, you can take different amounts and still invest and look at those accounts. So again, if we wanted to write this as a function, a of t, to represent the $50,000 account, we had that starting amount, and we would multiply by 1.05 to the t to express that amount. Now, if we talk about this as a graph, if we look at the graph of this, so we take our calculators and we plot this time our starting amount, which is 55,000, 1.05 to the t. In this case, we'll just call that x. And they're kind of helping us out because we can look at the table they are giving us. These are kind of our x values and our y values. This is going to allow us to set our window. So we are going from 0 to 15 years for our x's. Each year goes up by 1 at a time. And our y values, we start at $0 and we are going up to 120,000. And then notice the scale on this one, we are going up by 10,000 each time. And what we could do then is look at this graph and notice that we have this increasing graph over these course of these years. So if we look on here, we kind of can see that shape of our graph in the window. Now, if we look at this graph after about 10 years, we see that our account has about 81,000, just a little bit over 80,000, but just over 81,000 after 10 years. And if we think about the time it's going to take her to double her investment, aka when is it going to equal $100,000? Well, if we look on the graph for that, 100,000 is right here at about 14 years. Now the graph can only show us so much on that. We can find some exact amounts though using the graph or the equation. So for part A, if we wanted to find the exact value, we could plug in after 10 years to see again what our value would actually be. So if you go under actually this the second trace, there's this calculate menu. You can calculate a value. So if I want to plug this in for after 10 years, it's showing me again I have a little over $81,000. This one, $81,444.73 on that one. Now for part B, we're basically trying to look again, when does our graph equal $100,000? AKA, when is this going to equal 100,000 on this? Well, if we take our graph and we go back to the y equals menu and we look for 100,000. And what we can do is if we look at this graph, we can look for the intersection between them. So again, second trace, option 5 is intersect. And if we scroll over, we can get a little bit more of a precise estimate on when these are actually going to intersect so that we see when it hits 100,000. So if you scroll on top, hit enter a few times, we see it just about 14.2 years is when we're going to see that overlapped of the intersect between our two graphs. Okay, now we also could solve this part algebraically, because if we take this equation and we start to isolate to get t by itself, we would start by dividing both sides by the 50,000. And what we're going to notice is we get 2, oops, I forgot the t here, it's going to equal the 1.05 to the t power. And we're going to talk a little bit more about this in the upcoming lessons. But what we could do is we take the common log of both sides. So we have log of 2. And what this allows us to do is write that exponent of t out front. And then last but not least, we can divide again the log of 2 divided by the log of 1.05. And we could again see that we're going to get about 2. So log of 2 divided by log of 1.05. And again, we see that 14.2 for our value of t. All right, now, if we look on to the next page, we see, again, a little bit more about our formulas. And again, we see here that the starting value that we are using each time is 50,000, and that's what we call our principal value. That's, again, our initial amount is our principal value. And what you're also going to notice if we check out this graph is that this is also going to always be your y-intercept. All right, for these graphs, the 50,000, we have 10, 20, 30, 40, 50. That's our y-intercept. And then we have our interest rate. In this case, this is a growth factor because we are adding on this to our initial rate of 100%. There is also something that is known as the decay factor, and that's when we would subtract our percentage away from 1. So that value would be less than 1 if we were decaying. So be aware that that also will happen. And overall then, our formula for this, we say that our amount is found by taking our principal amount and then again 1 plus r to the t value for a growth. Again, a decay or a depreciation, our graph would have a 1 minus because we'd be subtracting away the rate. Now, something that we are going to notice is, let's say that Margaret instead intends on only investing $30,000. So she changes things up, same account, however, she has less money. And what she wants to know is, will her double time take any longer if she only invests $30,000 as opposed to the $50,000? Well, what we're going to notice is if we do the same process that we did before, if we divide both sides by that coefficient so that we get 2, and we have 1.05 to the t. Again, if we take the common log of both sides, what we're going to notice is we end up with log of 2 divided by log of 1.05. So our value still is 14.2. So what we're going to notice is that no matter what happens with these each time, our doubling value is the same for our same interest rate of 1.05, aka 5%. And why is this? Okay, why does this keep happening? Well, what's basically happening is if I have a principal amount that I'm multiplying by 1.05 and I'm looking for the time it doubles to that principal amount, well, if I divide over the principal amount, each time it's simplifying to be this same little equation to solve. So things are canceling out. So you're going to notice that that double time is the same regardless. All right, couple questions to stop and try on your own with the check your understanding. All right, now if we move on to our last set here, this time we are checking out basically 3 comparisons. What if we start with that 50,000 in the account, but how do things get affected if we change this up so that we would have B of T that is only going to start with 25,000, or if we have C of T that only starts with even less money, 10,000. Again, how are these affecting our rates each time, or what are we noticing? Well, whether we have our $50,000 account, our $25,000 account. So again, same multiplying factor 1.05 to the x this time. Or if we even look at the $10,000 account, oops, 1.05 to the t, in this case x. Okay, again, some things that we're noticing is for all 3 graphs, our y-intercept is the same, is that starting value 50,000, 25,000, and 10,000 end up being our principal value, aka our y-intercept. And as time goes on, the graphs are increasing as time goes on. So we can see that again, we will still be increasing our money each time over, and the y-intercept is the principal amount. Increases as time goes on. And again, with that analysis, okay, if we look over at the table even as well with these, okay, we see that growth happening over the course of 10 years. We still even see some of the ones that we looked at before. All right, now, last little part here today is going to talk to us about question number 19. And question number 19 is asking us to not only compare our parent function of the exponential, but what happens if we negate. So what we're going to do is let's make our A value 10 and our B value 2 for each of these. And if we clear all this out, so clear 1, 2, and 3. Again, I'm just going to make my starting term 10, my multiplier 2 to the t, or in this case, x power. And then I'm going to do the exact same a and b values to compare. However, I'm going to bring this to the negative x power. And I'm just going to zoom 6 to reset my window. And we can see these two graphs. The blue graph, which is our a times b to the x, and our red graph, which is a times b to the negative x. And what we're noticing is if we go from negative infinity to positive infinity, which graph is increasing? Well, that's going to be our parent function graph, right? F of x. And as we look at the graph here, left to right, which one's decreasing? That's going to be the g of x graph. Now, which of these has an x-intercept at a comma 0? Well, if you look at the graph, neither of these officially touch the graph at a comma 0, right? It's never actually touching 0. It's just getting infinitely close either graph. So neither of them are actually going to touch the x-intercept. However, both of them are going to have a y-intercept. And we notice since both of them have a starting principal value of 10, if we look at our graph, both of them are going to touch 10 up here as their y-intercept. Now, do they have a horizontal asymptote at y equals 0? Yes, they both do. They're both approaching that and converging. And again, both of them are going to have all real numbers. There's no official breaks in the graph. From negative infinity to positive infinity, they're either getting really close to 0 or going towards positive infinity. Both of them only have y values above y equals 0. Neither of them are going to dip below, if we look at this graph, y equals 0. So they're not below that. All right, thanks everyone for watching and looking into the beginning of our exponentials. We will work more with these formulas in class.